So welcome back to this Python learning journey, where the goal and objective is to learn and master Python over the next 100 days. Today is day 48. We're almost 50% out of the whole 100 days learning journey. While looking at the whole career track, which is the data analyst in Python career track, we're almost 50% also out of the 9 courses that we need to cover to master the basics of Python for data analysis. So welcome back to the channel, and we are on the course of statistics in Python, which is introduction to statistics in Python, and we are on the third chapter, which is the normal distribution. So from chapter 1, chapter 2, it look like basic statistics in Python and different statistical analysis and statistical concepts. So you need to learn to be a Pythonista. So without further ado, let's jump back to learning and continue from where we stopped a couple of live streams ago. So I'll just start sharing my screen real quick so we can move ahead to the next lesson. So if you're looking to learn Python for data analysis, I'll encourage you to go to the live stream tab on the YouTube channel. Just go to the live stream tab. You see all the way from Python day 1, where we cover the Python basics, which is introduction to Python, list in Python, tuples in Python, and we did some data analysis and project also so far. So we just continue from this introduction to statistics in Python, where we've covered summary statistics and random numbers and probability with Python. So we're moving to more distribution and the central limit theorem, where it is time to explore one of the most important probability distribution in statistics, which is the normal distribution. You create histograms to plot normal distributions and gain an understanding of the central limit theorem before expanding your knowledge of statistical function by adding the Poisson and exponential and t-distribution to your report here. Definitely, you'll be needing all of this in your data analysis with Python. So it's just a good thing to learn Python as soon as possible. And definitely, I see a lot of job posts or a lot of job requirements that you need to have Python as a plus. So probably if you know Excel, Power BI, or Power BI or SQL, if you know Google Sheet or Excel, if you know SQL or probably PostgreSQL, MySQL, so Python is a plus as usual. So let's try and complete it over the next couple of 100 days and see what we can build with it. We'll just go to the normal distribution lesson and start immediately. Also, we have all these data sets to use. We have access to our data sets here. So to use for this lesson, we have this meal deals. That's what we'll be using. We've used this food consumption for chapter 1 and this meal deals for chapter 2. Hopefully, I'm going to be using this world happiness, the CSV data sets for chapter 3. So let's move ahead.
The next probability distribution we'll discuss is the normal distribution. It's one of the most important probability distributions you'll learn about, since a countless number of statistical methods rely on it, and it applies to more real-world situations than the distributions we've covered so far. The normal distribution looks like this. Its shape is commonly referred to as a bell curve. The normal distribution has a few important properties. First, it's symmetrical, so the left side is a mirror image of the right. Second, just like any continuous distribution, the area beneath the curve is 1. Third, the probability never hits 0, even if it looks like it does at the tail ends. Only 0.006% of its area is contained beyond the edges of this graph. The normal distribution is described by its mean and standard deviation. Here is a normal distribution with a mean of 20 and a standard deviation of 3. And here is a normal distribution with a mean of 0 and a standard deviation of 1. When a normal distribution has mean 0 and a standard deviation of 1, it's a special distribution called the standard normal distribution. Notice how both distributions have the same shape, but their axes have different scales. For the normal distribution, 68% of the area is within 1 standard deviation of the mean. 95% of the area falls within 2 standard deviations of the mean, and 99.7% of the area falls within 3 standard deviations. This is sometimes called the 68, 95, 99.7 rule. There's lots of real-world data shaped like the normal distribution. For example, here is a histogram of the heights of women that participated in the National Health and Nutrition Examination Survey. The mean height is around 161 centimeters, and the standard deviation is about 7 centimeters. Since this height data closely resembles the normal distribution, we can take the area under a normal distribution with mean 161 and standard deviation 7 to approximate what percent of women fall into different height ranges. For example, what percent of women are shorter than 154 centimeters? We can answer this using norm.cdf from scipy.stats, which takes the area of the normal distribution less than some number. We pass in the number of interest, 154, followed by the mean and standard deviation of the normal distribution we're using. This gives us about 16% of women are shorter than 154 centimeters. To find the percent of women taller than 154 centimeters, we can take 1 minus the area on the left of 154, which equals the area to the right of 154. To get the percent of women between 154 and 157 centimeters tall, we can take the area below 157 and subtract the area below 154, which leaves us the area between 154 and 157. We can also calculate percentiles from heights using norm.ppf. To figure out what height 90% of women are shorter than, we pass 0.9 into norm.ppf, along with the same mean and standard deviation we've been working with. This tells us that 90% of women are shorter than 170 centimeters tall. We can figure out the height 90% of women are taller than, since this is also the height that 10% of women are shorter than. We can take 1 minus 0.9 to get 0.1, which we'll use as the first argument of norm.ppf. Just like with other distributions, we can generate random numbers from a normal distribution using norm.rvs, passing in the distribution's mean and standard deviation, as well as the sample size we want. Here, we've generated 10 more random heights. Your turn to practice using the normal distribution.
Okay, since most of the real-world data sets fall into the normal distribution, that's interesting. So other distribution we've been learning so far, like the discrete distribution, what about the other one? Can't remember right now. Are quite not needed. So let's see distribution of our meal sales. So that's what we'll be using. So I'm making use of this our meal deal sales. I'm just going to create a new Jupyter notebook for this chapter 3. So this was for chapter 1 and chapter 2. Let's create a new one for chapter 3. Or I also launch this chapter 2. I just need to copy some information there. Okay. So I'll just rename it. How can I rename it to? So this chapter 3 is based on s- central limit theorem, chapter 3. Okay. Let's name it after that. Central limit theorem, chapter 3. So I just want to import this library because this was all the libraries we've been making use of. So we learned all about pandas for data manipulation, NumPy for uh, calculation, basic statistics. We also learned about matplotlib for visualization, and this sci-fi stats is also for statistics calculation. So let's import those libraries. Since we are still making use of the Amil deals, Amil dataset, this Amil deals dataset, I'll leave a link to download this dataset under the YouTube description, so you can also practice also. So we have it here. So I'm just going to just copy this line of code to connect to it. Okay, we're reading Amil deals now. Read Amil sales. Amildews. So just read that. That's good. So if you be following along, you know these are the normal thing you do first before connecting to your data sets. Oh, oh, okay, okay. So I could just come back here, just call on sales and see what we have here. Consider this is their mail deals data set, just the product, the client, the status, probably the client was one or not, the amounts one, number of users that we just have here based on the data sets. So let's just do dot edge to view very few lines of the data set. Now let's go back to the instruction to see what we need to do. Since each deal I may worked on, both won and lost was different. Each was worth a different amount of money, as we can see in the data set here. The amounts, the deals won, either won or lost, they're worth different amount of money. So let's see what we need to do there. So these values are stored in the amounts column of our meal deals. So as part of our meals performance review, you want to be able to estimate the probability of him selling different amounts. But before you can do this, you need to determine what kind of distribution the amount variable follows. Okay, so we need to know what kind of distribution this amounts column follows using either probably the normal distribution. So both pandas as PD and matplotlib as PLT are loaded and Amil deals is available. So create a histogram with 10 bins to visualize the distribution of the amounts. So we need to create a histogram with 10 bins to visualize the distribution of the amounts. Let's say distribution of Amil deals. We're going to run the same line of code here. I'll just start from here first. So to show the distribution, it will be plt dot east. So we want to show Amil deals, Amil underscore deals. We want to work with the amounts column. So we after the amounts column. So the number of bins that we want is 10 bins. So let's run the line of code for us to see what we have here. You could just show the other stuff. Ooh, name amount is not defined. Amount AMOUNT. Oh, I need to put it in quotes. Sorry about that. So you can see as Amil deals follows definitely the normal distribution. So if we could just let me just copy the line of code here and see. So the amounts column, this amounts column. Ooh, Amil, oh, mine is sales here. Okay, mine is sales. So my data frame here is sales. I named it something different here. You see, it is sales. Because it is definitely normal distribution. For some, I think the lowest number here is 2,000, or the highest amount is 10,000. So you could just add, let me just add some little information here to the charts. You could say the edge color, the edge of the histogram should be black. Should be equals to black. Then the alpha, that is how bright the chart should be. That should be 0.7. Let's run the line of code again. You can see each bar is different. You can see this definitely probably on 8,000, 2,000, 3,000, 4,000, 5,000, 6,000. So you could just also do some formatting, but we don't need all that for now. You give the UI label a title. Let us just move on from the little we've done. So Amil, did you call Amil deals.ist? Let's see. So I use the same. I use Amil deals ist plot plt.ist. Okay, let's see. Only a different line of code should solve the answer. Amil deals.ist. I did plt.ist. Okay, see the same thing though. Dot Instagram. Then it beats. Let's run the code. Oh, okay. I just love to run this line of code again. So to see if it is going to show me the same result or different results. So this one is going to be sales amount dot is, then the bin size is 10. We have this similar results, but just different stuff was returned here. If I now add this edge color, let me add this edge color here also. Let me see if it's going to. Oh, so you can see, so different line of code, but same results. You can say PLT dot is sales amount. You can also do a mail deals dot is. We have similar results. That is the most important thing. Okay, which probability distribution does the sales amount most closely follow? Definitely the normal distribution. Fabulous work. Now you have visualized the data. You know that you can approximate probabilities of different amounts using the normal distribution. So let's see how to do that. Okay, so what we need to do here is the solve this for challenge. Probabilities from the normal distribution and simulating sales under new market conditions. So which market is better? Then we move to the central limit theory. Let's solve this first. So since each deal Amir worked on, both won and lost, was different. Okay, I think was different. Each was worth a different amount of money. So these values are stored in the amounts column of Amir deals and follow a normal distribution with a mean of $5,000. Let's see the mean. You just check on the mean. So the center here, yeah, that's correct. The center here is $5,000. And the middle number, the lowest number is 0. The highest number is $10,000. So the mean is $5,000 with a mean of $5,000 and a standard deviation of $2,000. So as part of its performance metrics, you want to calculate the probability of a meal closing a deal worth various amounts. So num from numpy, the start is imported as well as pandas as PD. The data frame meal deals is loaded. So we have our data frame here to use. Let's see how to solve this challenge. So I need to import a num from numpy. I think I have that is imported already. Let me check. Okay, what I used last was uniform and binom. So let's say from scipy dot stats import num. That is the normal distribution. We have that already. Now let's move on. So we're going to be using this num to work with a normal distribution, which is the amount. So let's follow the instruction and see what we need to do. It now says what's the probability of me closing a deal worth less than $75,000? Less less than $45,000. No, that is $7,500. That's interesting. So let's take a peep at. So that'll be num.cdf. So so we know the mean amount to be $5,000 there. The standard deviation is $2,000. So it will be num.cdf, open brackets. So probably that means we close the deal on less than $5,000. That will be 7,500 or $7,500 rather. $7,500, comma. Then the standard deviation or the mean amount is $5,000 there. $5,000. Then the standard deviation is $2,000. $2,000. Let's run the code. The probability is 89%. Okay, let's see. The probability is also 89% based on the data that we have here. Let's submit the answer and see. So that is correct. So probably that Amir is going to close a deal uh less than $7,500 is 89% using the num.cdf or library there. So what is the probability of Amir closing a deal worth more than $1,000? It is $1,000. So that definitely should be 1 minus the normal distribution of him closing $1,000. Okay, let's see. 1 minus, definitely 1 minus. We num.cdf $1,000. Is it less than $1,000? And the normal distribution or the mean is $5,000. And the standard deviation is $2,000. Yeah, that should be 1 minus that since it is less. So that is 97%. That's interesting. Oh, we got that. So let's do the same thing here. Probability of due greater than $1,000. That is 97%. So the next should be probability of a deal, closing a deal worth between 3,000 and 7. So between two different. So that should be probability of the 3,000 minus the probability of the one of 7,000. So that's how this should be done. Since it is between two numbers, that'll be num.cdf. Probability of him closing 3,000. The highest is 7,000. So 7,000 will come first. Then the mean is $5,000. And the standard deviation is $2,000 minus the probability of num.cdf Minus probability of him closing 3,000. Standard deviation is 5,000 and mean, or the mean is 5,000 rather, and standard deviation is 2,000. So you can just run it like this. Let's see. That's 68%. Let's submit and see. So we knew that. So what's the last one there? So that is 68%. So the last challenge there is what amount will 25% of our meal deal sales be less than? What amount will 25% of our meal deal sales be less than? Ooh. Will 25% of our meal calculate the amount that 25% of deals will be less than? Or that should be that we should use num.ppf here since it is percentage num.ppf. So 25% that is should be 0.25 mine comma the standard deviation. The mean is $5,000. Since it's 25%. Okay, let's see. Mm, okay, $5,000. And the standard deviation is $2,000. Let's see. So the amount that 25% of deals will be less than should be over $3,000. Let's see if you are correct. Oh, great, we nailed it. So that's actually use this num dot ppf or this is so what we did we actually use this start function, this library scipher.start import num to perform all this calculation that you are seeing here. So see we're mentioning num over and over again. So that's how straightforward these calculations are. So Nifty normal distribution usage, you know that you can count on a meal 75% every time to make a sale worth at least $3,600. So this information could be useful in making company-wide sales projection. Oh, that is interesting. Great, we've been learning quite a while now. So let's see what we need to do here on this last challenge. Simulating sales under new market or conditions. So simulating sales under new market conditions. So the company's financial analyst is predicting that our next quarter, the worth of each sale will increase by 20% and the volatility or standard deviation of each sales worth will increase by 30%. So to see what our meal sales may look like next quarter under these new market conditions, you simulate new sales amounts using the normal distribution and store this in the new sales data frame, which has already been created for you. So in addition, num from scipy.stats are pandas as PD and map.lotlib.pyplot as PLT are loaded. So let's calculate the new average amount. So we have a data set called new sales already. So we want to simulate the percentage increase based on the new market condition. Okay, let's give it a shot. It says currently our meal's average sale amount is $5,000. Calculate what its new average amount will be if it increased by 20% and store this in new mean. So if the amount increase by 20% and store it in new mean. So the amount has increased already. We don't need to mention the percentage. Okay, let's give it a shot. Okay. Let's say the new mean should be the new sales rather. So new sales, the data for new sales is equal to the amount column dot mean. That should give us the new mean that we need. Dot mean. So that should give us the new mean. If it increased by 20%, I'll store this in new mean. That should give us the new mean. Let's run this line of code. New sales is not defined. But we have new sales. Oh, come on. Let's see. New sales. So it is saying that it don't see new sales, but we know that it is there already. So let's continue. To calculate new standard deviation, so new standard deviation will definitely become is the same thing. New sales, the amount column. So we know I mean average amount is 5,000. Calculate what is new average amount will be if increased by 20%. So, but we know that the average amount is $5,000, right? Okay, that means we don't know what we don't have is the new sales. If we just do like this, let's do another approach. $5,000 multiply by 20%, which is 20% increase. That's 0.2%. So let's see what we have here. So by 1.2. So it is 20%. So yeah, 20% is. Let's run this line of code again. Mm, Let's see the error we're having. Yeah, so we know that. So it will be 5,000 new sales. To fix this, you need to calculate new mean directly based on our means current average sale amount. And I'm trying to derive it from new sales. Here is the corrected line of code. That will be 5,000 times 1.2, which is 20%. So it's got this is $5,000, then 100% of $5,000, then 20% of the new sales. That will give us the new sales. So that's why we are seeing 1.2 here, which is 120%. So there's a is increasing by 20% more from the previous 100%. So definitely the new standard deviation is going to be, our mean current standard deviation is 2,000. Calculate what is new standard deviation will be if it increased by 30% and store this as new standard deviation. That should be the current standard deviation of 2,000 multiply of 2,000 multiply by 1.3% to give us 30% increase of 100%. So now simulate 36 new sales. So we need to create a 36 new sales. Okay, create a variable called new sales which contains 36 simulated amounts from a normal distribution with a mean of the new mean and a standard deviation of new STD. Okay, so new sales is going to be num dot rvs, rvs, open brackets. Our new sales is going to be so our new mean is going to be then standard deviation new STD. Then the size that we want to create is 36. Size is 36. based off of the new information that we have. So say PLT.is. Now plot the distribution of the new sales amount using a histogram and show the plot. PLT.is. That should be new sales. So we have that here. Sales then amount. So that's what we need to do. PLT.is. New sales. Then the amounts column. So let's see PLT.show. PLT.show to visualize the results. Ooh. Let's get help on the error. I didn't mention the amount column there. Oh, probably it is only just one record that we have here. Interesting. So you could see, now let's simulate the same. We could actually simulate the same thing in my Jupyter notebook here. Let's see. So the first line of code says calculate the average amounts based off of the new amounts. Let me just cut this out. I want this line of code. This is the new standard deviation. So this is the new sales. We just call on new sales and see what we have here. If you have an array of sales record there, see. If you create an histogram of the sales record, this is what we have also. So since this is a random number, we don't expect it to be the same thing, but it is similar. It's quite different right now. I'm just trying to document my knowledge here, so I can always come back to it. Okay. So this is what I'm just trying to do here. So I can always reference this notebook back when I need to refresh my knowledge. So finally, simulate new sales. So that's what we did here. Okay, with a mean and a standard deviation. Just like to make the record smaller, so I can create a variable called new sales, which contains 36 simulated amounts from a normal distribution with a mean of new mean and a standard deviation of new STD. That's what we did here. So we nailed this challenge. Let's submit and see. So successful simulating, although the average sale amount went up, the variation also increased. So it's not straightforward to decide whether these sales are better than its current ones. In the next exercise, we will explore the effect of higher variation. Interesting. So which market is better? Oh, let's solve this last challenge. So which market is better? So the key metric that the company uses to evaluate salespeople is the percent of sales they make over $1,000, since the time to put into each sale is usually worth a bit more than that. So the higher this metric, the better the salesperson is performing. Recall that our most current sales amounts have a mean of $5,000 and a standard deviation of $2,000, and our most predicted amounts in the next quarter market have a mean of $6,000. If I check Yeah, that's true. Closely a mean of $6,000 predicted and a standard deviation of 2,600. None from SciPy is imported. Based on only these metric percents of sales over $8,000, does our meal perform better in the current market over the predicted markets? Hmm. Can we run the line of code here? If you have to look at it, okay. So which market is better? If you can run the standard deviation of each scenario, let me see if it is possible. If I say num.cdf, the current standard deviation is, let's see, if you say this current market is $8,000, so $8,000, that is the what they are using to know if the salesperson is doing well. Then the current mean for that is $5,000, and the standard deviation is 2,000. There's no way I can run this line of code here. Compared to, you can see, so the output is 2.7%. What about for the one of, if the num.cdf, so if the amount is $1,000 and the standard deviation is expected to go to 6,000, the mean is expected to grow by $6,000, the forecasted mean, and the standard deviation is 2,600. So where is it doing better? Ooh, that means it's doing better in the current market. I'll probably go for the current market. So the current one is better. You can see that the predicted is 0.027, while the current one is making 2.7. So I'll go for the current market. Ooh, not quite. You can't compare the metrics in the various situations. So what can I use to compare it? What can I use to compare it? Is it not CDF? Okay, hold up. Is it PPF or CDF? We're going to use CDF if I'm not mistaken. It says not quite. You can't compare the metrics in the various situations using num.cdf. So all I know is okay. Let's take a hint. That will be 1 minus num. Remember that you calculated the percent of sales over 1,000 in the current market using 1 minus num. You can calculate the percent of sales over in the predicted market by adjusting the mean and standard deviation in the num.cdf call above. Okay. So the current will be 1 minus num. Okay, let's see. Okay, let me see. Let me see this. 1 minus num. That's on the code. That is 1. You can calculate the percent of sales over 1,000 in the predicted market by adjusting the mean and standard deviation in the num.cdf. Okay. So 1 minus num based on the current market. Are you going to get the same results? That's 0.97. Definitely still the current market is still the best answer. Oh, okay. So maybe the predicted market I say not quite. What's not the answer? Is it performing well in both markets? No, no, no. So okay, great work. In the current market, Amil makes sales over 1,000 about 97% of the time and about 97.3% of the time in the predicted market. So, okay, the predicted market is 97.3, which is correct, but the normal market is 100% of the time. So I'm not visualizing the data very well. So if we use 1 minus norm for the prediction, okay, oh, probability is kind of tricky. So great work. In the current market, Amil makes sales over 1,000 about 97% percent of the time, which is over close to 100%, and about 97.3 in the predicted market, which is this market here, 97.3. Okay, okay, that's interesting. But I was curious. Let me see. Let me see this result here. I was curious, why must I use 1 minus rather than I don't know why I was getting that error. Why can't I use .cdf? I need to understand why I can't use this .cdf in this situation. Okay, let's see. That means the two markets. Oh, that's correct. So I have to use 1 minus to correct that. So it has to be this 1 minus the num.cdf, not using just the num.cdf to compare both markets. Okay, okay. You learn every day. So now we're moving to the central limit theorem. So that will be the next challenge on day 49 live stream. So let's stop here for today. We've cracked our brain enough just for probability. All right, so that will be the end of the live stream for today. If you found knowledge or if you find this exciting learning Python and playing with code around, do well to support the channel by giving the video a thumbs up, hit that subscribe button, and I'll see you on the next video on the channel and on the next live stream. Let's get back to work. Have a wonderful rest of the day.